Listen to me very carefully.
Robot hands are notoriously hard to make. They lack the dexterity most of us take for granted. Did you have that one kid in class that could spin around his pen in his fingers? They just figured out how to make robotic hands do that perfectly. What was their secret? Well, the people behind this project were the same team that brought us Voyager, the Minecraft AI agent that runs around Minecraft, learning, improving, and constantly getting better. They used ChatGPT, or more specifically GPT-4, to power this Minecraft AI, and it worked beautifully. Now they decided to test if GPT-4 can train a robot hand to do complex tasks. And again, it knocks it out of the park. Now, if you've been following this channel, you've seen examples where AI, more often than not GPT-4, is capable of improving itself or other AI models for robotics or image generation or whatever. It's better able to do that than humans can. Here's a quote from Dr. Jim Fan, one of the people on this project. I think I mentioned him on this channel a few million times. Here he's saying that the system driven in part by GPT-4 is better able to train these robotic hands than humans can. He says this gives me deja vu back to 2016, where AlphaGo made brilliant moves that no human Go player would make. AI will discover very effective strategies that look alien to us. Alright, so let's start by looking at this post by Dr. Jim Fan. He quickly goes over some of his findings and kind of highlights and summarizes some of it. So, can GPT-4 teach a robot hand to do pen spinning tricks better than you do? I'm excited to announce Eureka. So Eureka is the open-ended project that this whole paper is about. So you'll see that GPT-4 is a big part of it, but there are other big parts of it that make this work. So Eureka is an open-ended agent that designs reward functions for robot dexterity at superhuman level. It's like a Voyager, the Minecraft AI, in the space of a physics simulator API. By the way, the team behind Eureka and Voyager, so they're part of NVIDIA. Now this is put out there for research purposes, meaning Eureka and Voyager. So it's sort of outside of NVIDIA, it's not sort of under the umbrella of the company, it's for research purposes, but a lot of this is backed by NVIDIA. All right, so here's that video. As you can see, it's doing various spinning tasks. How many of these could you do? I could do 0 of these. So in robot learnings, LMs are good at generating high-level plans and mid-level actions like pick and place, but fall short of complex high-frequency motor controls. The Eureka moment for us, that's very good, is that reward functions through coding is the key portal where LLMs can venture into dexterous skills. So we'll go through exactly how they started this out. And so they're saying first, by using the raw Isaac Gem environment code as a context, Eureka can already generate usable reward programs without any task-specific prompt engineering. This allows Eureka to be open-ended generalist reward designer with minimal hacking. So here's Isaac Gem. So as you can see here, you kind of have this simulated reality where a bunch of robots are crawling around, kind of learning how to walk, etc. Here's a sort of a robotic arm that's screwing in this thing. There's, as you can see, 4 of these guys around. And I covered this one before. So here's kind of flipping this cube to get the proper alignment that you want. So for example, when this is blue, it's trying to get it to blue. When it's white, it's trying to get the white side up. And as soon as it gets it there, right, this switches to the next thing. So it completes its task. As you can see here, there are like rows and rows of these things just training and figuring out how to do it better. So basically you can think of this as a simulation where you can have like thousands and perhaps millions of these things learning in tandem, figuring out how to do it better, and where time can basically run faster than in real life. This is always a fun watch. This is like these little humanoid shapes that are learning how to run. Watching them try to figure out how to run when they're first learning is hilarious, I have to say. So I'll include this page in the comments if you want to take a look at it for yourself. So this is the abstract of the paper. And here are the tests that were run with the reward function that was written out. So here's it's testing the ability to turn the cube in the right direction depending on which sort of color you need to be shown up. Basically, it has to match the 3D position of this cube in its hand. So as you can see here, it's kind of using its fingers to flip it in the correct direction. A spider-like figure learning to walk. The robot dog learning to walk. Whatever this is, it's some sort of a table with, oh, it's trying to catch the ball on like a plate. catching an egg on a plate. I guess this is what this is. And here it's trying to maintain the upright position of this thing. So if it starts falling this way, it has to like roll this way and kind of like try to maintain this in an upright position. I mean, it's obviously very good because nothing's moving. Opening a drawer, learning to walk for a humanoid figure. So this is like a drone that's flying around. How to arrange its little propellers, its motors to hit a certain position. And of course, the pencil spinning trick. Or in this case, it's trying to just match the 3D position of this object. And there's many, many more. All right, so let's take a look at the paper. So this is Eureka Human Level Reward Design via Coding Large Language Models. And so again, they point out here that Eureka, this sort of system, outperforms human experts on 83% of the tasks and an average improvement of 52%. How they did that? Let's take a look. So this is sort of the broad overview of what it's doing here. So let's say we have our task description. To make the shadow hand spin the pen to a target orientation. And this is sort of the code to create this environment here. So the coding LLM GPT-4 in this case, it goes to work creating a reward for how to do this. So you might have certain penalties, you might have certain rewards, but basically it's trying to make a reward function for how to do this. That would over time make the hand approximate the pen spinning motion. And we take that reward function, we throw it into the GPU accelerated reinforcement learning, the Isaac Gym. This always reminds me of that Dragon Ball Z. They had the time compression chamber, the hyperbolic time compression chamber, where they would go in there and train for like 1,000 years in the span of a day. This is kind of like that. This is a Dragon Ball Z style training. Then we get the results out of here, we put it back into here, and GPT once again attempts to create a better reward, a better sort of reward code to try again. And so this goes in a loop in this sort of diagram without any human feedback at this time. It's trying to get better and better at making the shadow hand, as they refer to it, spin the pen to a target or orientation in this case. Eureka stands for Evolution-Driven Universal Reward Kit for Agent. And so the results were that it achieves human-level performance on reward designs across a diverse suite of open-sourced environments, including quadruped, quadcopter, biped, manipulator, etc. And Eureka autonomously generates rewards that outperform expert human rewards on 83% of the tasks, an improvement of 52%. So this is the what, and this is why it's important. It solves dexterous manipulation tasks that were previously not feasible by manual reward engineering. So a human being couldn't manually sit there and type up this reward that solves these hard manipulation tasks. And this Eureka, this evolution-driven AI GPT-4 powered reward code writer, is able to do that. We demonstrate for the first time rapid pen spinning maneuvers on a simulated anthropomorphic shadow hand. Yeah, this is absolutely incredible. Not only is this a big milestone, but this milestone was accomplished autonomously through AI working in a loop to continuously improve itself. And it enables a new gradient-free, in-context learning approach to reinforcement learning from human feedback. Now, there's a lot of AI models that are trained with gradient descent. Sort of over time, as its training is getting better and better and better and better at something, and that's not always applicable to everything. Number one, it can be very expensive from a computational perspective. It might cost a lot of money, a lot of compute to make that happen. And there are certain situations where it simply just doesn't really work because there's no straightforward path from bad to good. It's a little bit more complex. So creating something that doesn't rely on gradient definitely opens up possibilities. I'd love to see Dr. Jim Fan unpack this a little bit more, what exactly this allows us to do, but this does open up some doors in terms of where this can be used. All right, so really fast, I think it's going to make sense for us to jump past the end of the paper into the appendix where we have like the initial system prompts for GPT-4. I think that might help shine some light on how they're doing this. So really fast, for people that are not familiar, there's something called PyTorch. So it was developed originally by Meta, Facebook, but it's open sourced and looks like it's now part of the Linux Foundation umbrella. It has a wide variety of tools to build, train, deploy various machine learning models. So if you see references to PyTorch, that's what they're talking about. So the initial system prompt for GPT-4 And so they're saying at a high level, Eureka only instructs generic guidance on reward design as well as simulator-specific code formatting tips. So it's saying you're a reward engineer trying to write reward functions to solve reinforcement learning tasks as effective as possible. Your goal is to write a reward function for the environment that will help the agent learn the task described in text. Your reward function should use useful variables from the environment as inputs. As an example, and here it gives an example of what that would look like. And then it also talks about, how to make it compatible since they're using this. And then once this runs, I guess, once it comes back, now we have the reward reflection and feedback. So we trained a reinforcement learning policy using the provided reward function code and tracked the values of the individual components and the reward function, as well as global policy metrics such as success rates and episode lengths after every epoch, the maximum, mean, and minimum, and the minimum values encountered. And so sort of this is the output, the results from how well this reward function ran. That's the results from it. And so they're saying, please carefully analyze the policy feedback and provide a new improved reward function that can be better used to solve this task. And some helpful tips for analyzing the policy feedback. And so if the success rates are always near 0, then just rewrite the whole thing, rewrite the entire function. And if the values are near identical throughout, then that means that reinforcement learning is not able to optimize this component as it is written. And it gives us some possible troubleshooting things it can do. If some components are significantly larger, then you must rescale its value to a proper range. Now, whether you understand this at a very deep level or not at all, I think the big takeaway here is everything here is very generic. There's nothing really specific, right? Could you guess what task we're trying to train for here? Is it to make something fly or run or pick up or open a shelf? There's nothing here that is specific to any particular task. They're saying, well, if it's always 0, then just redo the whole thing. And here's some tips for dealing with these other sort of things, but very generic, very, very general, meaning that you can use something like this for pretty much any task that you're trying to solve. And prompt number 3 is just a formatting tip, best practices so it doesn't mess things up. Again, very general, can be applied to everything. There's nothing specific here for any specific tasks. All right, so with that, let's jump back to here and let's highlight some important things that they're talking about. So they're saying that there was prior work that did some similar things here that was using large language models to aid reward design. But Eureka is very new and different in a couple important ways. First of all, it's free of task-specific prompts. As we've just seen, those prompts don't contain any specific language about which tasks it's going to be suited to, right? You can use that for any of the things that I mentioned earlier, from running to flying to picking things up to closing doors, etc. And so Eureka significantly outperforms because it's able to generate and refine free-form, expressive reward programs. It uses the environment as context. It uses evolutionary search, meaning that it's that loop that we talked about where it keeps trying and trying and trying. There's this evolutionary search to find the best code, the best reward function, and then reward reflection. So this is that second part where we give it this is actually that prompt that we just read, this prompt number 2. Like, here's the results of your action, GPT-4. Make it better. How do we make it better? We give it this back to it and it rewrites it. And that part is called the reward reflection. First part, environment as context. The paper states reward design requires the environment specifications to be provided to the LLM, right? So here we try to explain to the LLM what the heck the environment is, what it's working with. And this paper proposes directly feeding the raw environment code as context. And this is intuitive for 2 reasons. First, coding LLMs are trained on native code written in existing programming languages. So we should expect their code generation capability to be stronger when we directly allow them to compose in the style and syntax that they are trained on. So normally we have code, and then here we have a human, and then here we have the LLM, the AI. And so the code is kind of translated by a human and then given into the LLM. So machine, human, machine. This says just X this human out, right? Forget the human. Just give the code to the LLM. Just let the machines do the work. Let them do the talking. This guy just makes it worse. And second, and more fundamentally, the environment source code typically reveals what the environment semantically entails and which variables can and should be used to compose a reward function for the specified tasks again, I mean, I think it's just let the machines use their brains to figure out the code. Don't try to like simplify it, or just give them the whole raw data and they'll figure it out. The next thing talks about evolutionary search. And so in each iteration, Eureka, so the entirety of the system, that loop that we talked about, samples several independent outputs from the LLM. So it asks GPT-4, hey, give me, a few different versions of the code that you're writing. Since the generations are IID, so this is independent and identically distributed. So basically they're all like unique generations. You can think of they're all different versions of it, let's say, for simplicity. The probability that all reward functions from an iteration are buggy exponentially decreases. So the thing is, if you ask ChatGPT for one solution, that solution may be buggy, right? If you ask it for two, the chances of all of them being buggy decreases. Ask it for 10, for 100, it decreases more. Eventually, the more you ask for, the more exponentially less chance of all of them being buggy, meaning that at least one is coming out, correct, working. So sampling just 16 of outputs contains at least one executable reward code in the first iteration. And then next we're talking about the reward reflection. So again, that's this part where once we run the code that GPT-4 has generated and we get sort of the how well it worked, we feed it back, we tell it, hey, here's how well it worked. How can you improve it? AKA, we're asking it to reflect on how well it did, how well that reward did. All right, so in the reward reflection, ChatGPT tries changing, and there's a couple things it can do to make the reward function better. Adjusting some of the parameters, changing some of the functions, adding new components, etc. And now let's take a look at the results. So the blue, as you see here and here, those are the Eureka. That's the full sort of architecture that this paper is about, using GPT-4 and that loop of reflecting on the code and trying it again, etc., etc. The purple line here is, humans. How well do we do when we try to create these reward functions? And as you can see here, the success rate, so this is humans and this is Eureka. As you can see here, it has a higher success rate immediately on various dexterity tasks. And there are certain specific tasks that it's much better at. So on certain ones, it's as good as humans, slightly better than humans, and here's a few where it's just a lot better, and some that it's, somewhat better. Here's another one where it's ever so slightly better than humans. Right, and as far as I can tell, there's none where it's worse. There's no blue line here that's underneath this purple line of where human sort of the normalized score is. So if you were ever wondering when AI is going to be better at training robots to do various tasks, at what point it will cross the human's ability to do that, well, it's October 2023, and yeah, we're there. And so we've talked about some of the results already, but Eureka outperforms human rewards. Eureka exceeds or performs on par to all the tasks. So yes, there's not a single one here that's underneath the human sort of standardized score. And the other sort of the best approach that we used to have, while it's comparable on low-level dimensional tasks, on like the simpler ones where you balance, when you have that thing standing upright and you're trying to balance it, while it's, comparable on those, it lags significantly behind the, on the higher dimensional tasks. And in contrast to this L2Rs, in contrast, Eureka generates free-form rewards from scratch without any domain-specific knowledge and performs substantially better. In these papers, when they talk about ablations or ablate, that means they take certain parts of the experiment and they see, like, if we take this part away or if we make this part worse, like, does that affect it? So here, you can think of it as like a downgrade or taking certain parts out. So here they downgrade from GPT-4 to GPT 3.5, and they, find that Eureka degrades in performance, which, we kind of expect that, right? GPT 3.5 is not nearly as capable as GPT-4, but it still matches or exceeds human level. Yikes. Yeah, so GPT 3.5 is still it seems like pretty good, exceeds human level reward writing, indicating that its general principles can be readily applied to coding LLMs of varying qualities. I feel like this is big because this is saying that it's nothing special to GPT-4. It's not like this is the magic sauce behind it. the principles that they use here can be applied to a lot of different coding LLMs. Then they also mention here that Eureka consistently improves over time. So as you can see here, with each iteration, it gets better and better. Even when it exceeds human level performance, it still gets better and better and better with each iteration. And so here, interestingly, they're talking about, so basically so let me see if I can write this out. So basically when you're starting, it might sample several different ways of starting, right? And let's say it finds that these are bad and these are, better. And so it keeps iterating on these and it tries again and again and again to see which one does better, right? It keeps iterating. So here they're trying to ablate, meaning seeing what happens if we have less iteration steps. So here they're performing only the initial reward generation step. And this is in case if you have a fixed number of reward function budget, meaning you can't do too many iterations. Is it better to do more of these evolutions or simply sample more first attempt rewards without the iterative improvement? And so they're saying that Eureka rewards steadily improve and eventually surpass human rewards in performance despite subpar initial performances. So in other words, that really the secret sauce, the thing that really works well is these steps. As it iterates and keeps trying again and again and reflects on what it's doing, tries again and again. This is what's really causing the big results. The consistent improvement also cannot be replaced by just sampling more in the first iteration, as the ablation performances are lower than Eureka 2 after 2 iterations on both benchmarks. Together, these results demonstrate that Eureka's novel evolutionary optimization is indispensable for its final performance. Again, that's kind of what I said here. It's this evolution, this iteration, the try again, see what worked and try again, see what worked and try again. The OODA loop, if you will. Orient, observe, decide, and act, and then do it again and again and again and again. That is the new thing, this evolutionary optimization, and that is indispensable. That's the thing that makes this whole thing work, the great performance work. And also, Eureka generates novel rewards. So it creates new things that we're not really seeing humans do. It's that whole idea of the AlphaGo, where it makes this crazy move that most people just don't comprehend. This is the wrong move. Did it make a mistake? For the people that are not aware, so this is AlphaGo. This is the greatest person that's ever played Go. I apologize if I'm not, I don't know the exact details, but he was the world champion. And this is the sort of the infamous move 37 that AlphaGo, so DeepMind, Google's DeepMind, trained its AI to play Go, and so this move that it makes right now is the thing that everybody thought so weird. Look at the people's expressions. Look at the expressions on their face when they make that move. They're like, this AI is, it's stupid. It's just screwed up. That was not the game-winning move, but it was a very strong move that only later did, we, the humans, figure out, wow, that was a good move. And it was a move that normally, when you're learning how to play Go, the instructors, the people, the teachers, they would tell you that's not a good move to make. Don't make that move. But since AlphaGo learned to play without sort of human involvement, it figured out that no, in fact, that's a good move. That's the move it made. Nobody told it otherwise, and it was an excellent move to make. And so this is similar. So the fact that it generates novel rewards, meaning that it does stuff that humans don't. And so these are the wins where Eureka wins. As you can see, all these blue circles, they're not correlated to human rewards. They're not correlated to the, quote unquote, the moves that the human would make. If you think of writing these reward functions as moves in a game, it's very different than that of human moves. And so as you can see here, Eureka mostly generates weakly correlated reward functions. So it's kind of similar to what the humans make, but we observe that the harder the task is, the less correlated the Eureka rewards. And this is interesting because a lot of the conversation right now is can the AI reason? Can it think? Can it understand? A lot of people are arguing about it, even though I don't know if we necessarily have these ideas, these terms really well defined. So it's kind of maybe a useless argument, but I wonder how this kind of plays into that. So the authors of the paper say, we hypothesize that human rewards are less likely to be near optimal. for difficult tasks, leaving more room for Eureka rewards to be different and better. So in other words, or this is at least how I'm sort of interpreting it, is that we're pretty smart up to a point, but then we're not able to solve the more hard tasks. And, sort of our ability we keep up with the AI, but then our ability drops off while the AI's ability keeps going. And so it creates new things that are so different from ours because ours are subpar, ours aren't as good. And here it's saying that in a few cases, Eureka rewards are even negatively correlated with human rewards, meaning that they're very different from how humans think what a human would do in that situation, but they perform significantly better, demonstrating that Eureka can discover novel reward design principles that may run counter to human intuition. And this is absolutely incredible, especially if you consider the fact that, again, this is GPT-4 kind of out of the box, right? This isn't some super secret AI that NVIDIA created just for, to do this. This is GPT-4, this is ChatGPT. This is the thing that you can get for $20 a month. Next, they say reward reflection enables targeted improvement. And so in another ablation, so another sort of test, how they can break this thing, what really affects it, what doesn't. So they do Eureka, but with no reward reflection, which reduces the reward feedback prompt to include only snapshot values of the various metrics. And so sort of averaged across all tasks, Eureka, the normalized score drops by 28%. And of course, they see much greater drop in higher dimensional tasks. So the harder task, the more and more important this sort of reflection becomes, this loop of, here's how it worked, try again. Here's how it worked, try again. The harder the task, the more challenging it is, the more important this is. And then Eureka with curriculum learning enables dexterous pen spinning. And so they're trying to see if Eureka can be used to solve a truly novel and challenging dexterous task. To this end, we propose the pen spinning. So this is kind of like the final thing, the exciting thing that they did. And they require a shadow hand, interesting name, to continuously rotate a pen to achieve some predefined spinning patterns for as many cycles as possible. So here they consider a curriculum learning. So from Bengio, so Yoshua Bengio in 2022 became the most cited computer scientist in the world. And so they're considering this approach. So the idea there is basically start with simpler tasks and move on to more complex tasks, similar to how a human being would learn. And so here the approach to break down the task into manageable components that can be independently solved by Eureka. Similar approaches have been found successful for other coding LLM applications to decision-making. Specifically, we first instruct Eureka to generate a reward for reorienting the pen to random target configurations. And this is what we see on this page. Again, all the links will be in the show notes, but this is what they're talking about. So this is when they're saying, figure out the reward function for having the shadow hand, which is this thing, sort of approximate the 3D position of this. So when it's, on its side, how do you get it to that position? And so over time, with however many, evolutions, with however many attempts, GPT-4 writes out this reward function, right? So that's step one. And then using this pre-trained policy, we fine-tune it using Eureka reward to reach the sequence of pen spinning configurations. And then to demonstrate the importance of curriculum learning, they also train a baseline policy from scratch, using Eureka rewards, but without the first stage pre-training. So without getting it to this point first, they're just going straight for it. And so the training curves are shown in figure 7. So as you can see here, they're 0, right? There's just no visible success with that. However, with the fine-tuned, it takes off really fast, and then that learning curve slows down a little bit, but man, that's a fast takeoff right there. So getting it here first, first figure out how to do this. Once you have this, then we try to get it to just spin as much as it can, and it looks like it quickly gets to was that 5 steps, 5 spinning cycles pretty quickly, and then slowly continues from there. In contrast, neither pre-trained or learning from scratch policies can complete even a single cycle. So even a single cycle can't be completed. Yeah, it looks like they're all just at 0 there. And they also have the pre-trained policies for a variety of different spinning configurations. All pen spinning videos can be viewed on our project website. Again, that's these little videos right here, or animations here. And so next section, we're talking about Eureka from human feedback. we went over that with this humanoid running, right? So, it's the idea that, let's say you're making a video game where you want the characters to, you want the AI to make the characters, walk. And so it spits out this and you're like, okay, no, this is not like a horror game or whatever this is, grip walking game. Let's, as funny as this is, we need something that looks a little bit more like a human being running. So we, keep saying thumbs down until it, starts kind of approximating, this is a little bit closer, right? Basically, this is showing that Eureka's reward assistant capability, meaning that it can be like an assistant that helps you write these reward functions based on what you're looking for. It doesn't have to do everything from scratch. You can be the human in the loop that, kind of thumbs down and thumbs up the things that it's doing. Human designers are generally knowledgeable about relevant state variables, but are less proficient at designing rewards using them, which makes sense. I mean, a kid can tell you this, this is silly, this is silly, this is silly, you know what I mean? And then say, okay, this is more normal, right? But they might not be able to write a code to train that function. But GPT-4 can, or Eureka rather, this whole model. And conclusion, we have presented Eureka, a universal reward design algorithm powered by coding, large language models, and in-context evolutionary search. Without any task-specific prompt engineering or human intervention, Eureka achieves a human-level reward generation on a wide range of robots and tasks. Eureka's particular strength in learning dexterity solves dexterous pen spinning for the first time with a curriculum learning approach. Finally, Eureka enables a gradient-free approach to reinforcement learning from human feedback, readily incorporating human reward initialization and textual feedback to better steer its reward generation. The versatility and substantial performance gains of Eureka suggest that the simple principle of combining large language models with evolutionary algorithms is a general and scalable approach to reward design, an insight that may be generally applicable to difficult open-ended search problems.